Uh, so welcome anyone who's watching this video, this recorded session. This is live interaction session 9. Today is 23rd September. We are almost 75% over in the course on applied numerical methods, ME97, course instructor Professor Malay Kumar Das from IIT Kanpur. Um I am the live interaction session TA, Shri Sahai Gupta. I'm a doctoral student at ISC Bangalore. Um, and yes, maybe a quick introduction about me. I'm from Agra. I did my bachelor's in 2020 from IIT Roper. If you would like to reach me out, please note my email address and you can reach me out generally between in the week between our sessions. That would be the usual approach to reach me out if you have any questions or something. Um, okay, let's do a small recap before we begin our session. So let's do a quick recap. Yeah. Yes. So, essentially speaking, let's quickly look at what you guys have been doing in the video lectures of the course. So, yeah. So this course is designed as a 12-week course. The first week, I would say the first 2 weeks were kind of introductory. The second week was associated with programming and stuff. So basic programming for people who are new to coding. I see that professor has also used Jupyter Notebook. I think this is the first session, first time this course was floated was how many years ago. So it is a quite a old course. Anyways, so I don't see any date as such there. Maybe it's there in the video lectures. Anyways, so now the real stuff started from week 3 where we discussed linear equations, basically linear algebra, then the eigenvalue problem. Um, then we went into interpolation, finite difference, and numerical differentiation. Uh, week 7 was on numerical integration and ODEs. Week 7 continued into ODEs, and when week 8, we basically PDs were discussed. And then I think week 9 is just over, which you have done case studies in modeling, non-dimensionalization, and validation. So I'm just reading these things out. Essentially, our live interaction sessions turned out that we didn't follow this course structure, this week structure. We did begin by some glimpse of numerical methods. Essentially, the big umbrella the numerical methods uh, cover. So basically, started with our discussion on the divide and average method, where we were trying to find the under root of a unknown, under root of a number, and the approach of how it can be done numerically. So that was there. That was essentially the first week where we discussed this thing. And then second week, as it turned out that most of us, so when we interacted, people who joined in week 1, a lot of people were quite interested in finite approximation methods. So yeah, hi Yashod. So I'm
Hi,
just
good
adding.
evening.
Good evening. I'm just adding Yashod into the call. So as I was discussing, so in the week 1 of the course, we saw that a lot of people were interested in finite approximation methods. So Yashod, we are basically doing a small recap before we start our session. Uh, so
Okay,
as
okay.
so as I was saying, so then the next few weeks went into finite approximation methods, basically trying to cover the philosophy of the method. And what we did was we picked a simple problem. a heat conduction problem, a steady state heat conduction problem, and solved it with three approaches. The finite difference method was the first approach. As I have mentioned multiple times, it is the most straightforward, most intuitive approach. And essentially, we are trying to represent a function with a set of or a series of functional values uh, at grid points so you define a mesh, and at different nodes in this mesh you just figure out the functional value, the best approximation you can. So the closest value you can find to that functional value, it's not that accurate, it's you don't get the exact functional value, but close enough. If your scheme is if you have set up your solution setup is fine enough. And then we went, and essentially uh, uh, what happens there is um, once you have written all your equations and you have brought all your grid points and everything into a system of equation, you realize at the end of it you need to solve this ax equals to b structure. So that we used scipy libraries to do that. uh, then we went into finite volume, where we were rather interested into conservation of fluxes rather than figuring out functional values. So in finite volume also we find functional values at centers of control volume rather than at grid nodes. And essentially two control volumes, adjacent control volumes share fluxes. And by that philosophy, what essentially happens is that you are able to ensure conservation laws at both global and local scales. So that is something that happens. Uh, a lot of it, a finite volume is kind of repetitive with respect to finite difference. The essential difference comes at the treatment of boundary conditions, where you kind of are not using um, say you're not using the boundary condition at such, but you're kind of crafting a flux boundary condition at these. You convert the boundary condition into flux boundary conditions. So if the imposed boundary condition itself is a flux boundary condition, then it's straightforward. But generally, if you have a Dirichlet type of boundary condition, then you have to do some work. And then that too, when you write all the system of equation, again you have to solve ax equals to b. So that again we looked at. And then we spent good amount of time in finite element method, the philosophy of it, of how, why, what is the logic of um, the residual approach, what are we trying to do, the logic of test function and basis functions, and essentially thinking of, or essentially the most primitive finite element method, why will it have a hat shaped test function or shape function kind of stuff. So that part of it we discussed in good details. So this I think went on with I think for the couple of weeks, so I think 3 to 4 weeks. And then there were discussions on questions from audience, something on big O notation, then TDMA, uh, and there from there like I think roughly two sessions or one session went into this, uh, and then the next session which I started discussing was on numerical linear algebra. So essentially, in the week 2 and week 3, or essentially week 4, the 3 weeks of these 3 weeks of the courses, we were dealing with linear algebra. And to just design a TA session around numerical linear algebra, I kind of started looking into a very prominent scheme or decomposition, matrix decomposition, what you must be familiar with, especially in the setting of solving ax equals to b. People are introduced with Gauss elimination, and that is what is done in this course as well. So people are kind of more familiar with decompositions like LU decompositions, and sometimes even if you have uh, eigenvalue problems or least square problems, you look into eigenvalue decomposition or QR decomposition kind of stuff. But a more prominent and very interesting, very nice decomposition is singular value decomposition. That is something that I wanted to discuss at length. Uh, and so I begin, but again, there were few questions which we wanted to discuss, like on the shooting method. How what is the philosophy of the shooting method? So we looked at that, and part of it was like part of our discussion was on how this Clausius equations actually do we arrive there without going too much into fluid mechanics. How do we essentially get this kind of setting? That is where we looked in. That is where we were working on, and then we again figured out the shooting method, and we did all those kind of stuff. There was another question of what eigenvalues mean physically, so that was there. Um, and then yeah, so then we continued our discussion on shooting method, and essentially then I continued on things like on showing off singular value decomposition and its application. So this is where we stopped. We kind of had spent roughly 8 weeks, not roughly, exactly 8 weeks on that. That is the whole recap of our 8 week series, and I wanted to do this twice in this course. Now maybe eighth session, ninth session, because we are 75% into the course. It is nice to recap sometimes. And once you'll do it one last time when we are finalizing the last like live interaction session, maybe we'll recap it once again. Then uh, so now we are ready to discuss, continue our discussion on singular value decomposition. Turned out that my I actually crossed the time by in the last lecture, so it went around like half an hour more than what it is supposed to be. It should not be that long. 2.5 hours is just too much. So let's see how maybe we'll pick it up from back. I was also going a little fast, so maybe I'll take a little feedback from Yashod. So Yashod, if you have watched few lectures, how is the speed? Is it too fast? Is it like I feel sometimes that I'm not kind of being very descriptive and kind of move on from things very quickly. What is your feedback?
So basically, so yeah, like too sorry to tell that, like because like since two lectures I was not attending because I was busy in some other work, so I could not attend your session. Still, only finite. I was there in this line sessions till the discussion of finite element method where we were discussing and finalizing those three variations. So till that point, I was able to capture like it was okay for me to grasp the topics which you were explaining and the doubts which we clarified in the session. So till that point, I feel like it was okay. Like later on, like two sessions I could not catch the live session because of unavailability of my time. So
That's okay.
yeah, yeah.
Any comments on the speed with which I go? The speed is fine. It's speed, right?
For me, it was okay. Like back then, like for when we were discussing the three different, like understanding the finite difference, finite volume, and finite element. So that I could grasp because I think I was having some little bit knowledge on that. So I think for me it was yeah fine.
And I'm
Yes.
presuming because you have joined, you have some questions to discuss, or you have something to discuss you would like to
Hello.
Yeah.
Yeah, like
So
yeah, one like few things I have doubt like so right now we are in the 10th week of the this course. So
yes.
one thing is like I was having this question like now somewhat like I am familiar with writing of this program of explicit implicit schemes.
Hmm. Yes.
So like it was like taught regarding doing for like two-dimensional taking a square plate, square domain and doing that analysis in like I think you will be also familiar with that. So my question is like how it can be applied to a larger domain.
But when you
So
say larger domain, you
larger
mean
domain in the sense different complex geometries, not only the square domain. here we are defining the domain like in the coding, like taking nx to some number as 100 and
Yeah.
the second dimension as 100. So that
Yeah.
comes
So
as three and
essentially,
different.
if
Yes.
essentially, if I look at it, if we talk in pure computational uh, mechanics term, essentially what you're saying is that we have kind of a structured grid, and which is not possible in a complex geometry setting. Is that what your question is?
Yes, yes, yes.
Right. So maybe I'll quickly, this is again, this follows back to our discussion on finite approximation methods only. And maybe it's good that you asked that. Let me just open up that paper, which I kind of like very much because, yeah, just for some reason. Let me just open that paper because it's properly given in there. So yeah, this one. Okay, so essentially, as you rightly said, uh, structured grid, or let's say, actually, it's it kind of splits the approach as with what I understand, because I am not a expert in solid mechanics, and even I can actually say I would hardly qualify as a novice, but as far as I understand. Uh, Solid mechanics basically tend to go to finite element methods, finite element methods, right? Whereas fluent or any fluid mechanics kind of stuff or heat transfer problems, they try to approach it from a finite volume approach. And now it is easy to actually visualize why complex geometry will not affect our treatment of numerical scheme. Um, in a finite volume approach, because essentially you are integrating over the volume. So no matter how complex your geometry is, it is a volume integral after all that you're doing, or area integral which you would be doing. So it is easy to actually visualize why a finite volume method will work in a complex geometry. Not that I don't understand finite element method to that degree that I can explain why finite element method work very well with complex geometry. So what you would have realized up to now is that you are kind of essentially dealing with finite difference in the entirety of this course, isn't it? Or have you come across some treatment with, like, where sir uses finite volume or finite difference? Is my
Mm,
understanding correct? It's
yeah, I
generally,
think so. We have only like gone through finite difference as
yeah.
now.
Yeah, and that is essentially because this is a like a first like a introductory course into numerical methods. As I said, finite difference is very easy to formulate. It is very intuitive. So and it works very well when you have a very simple geometry, when you want to illustrate, demonstrate the methods. Finite difference is the go-to method. Uh, so that is where that is actually the crux of your question. Essentially, we do not extend this. Whatever we have learned in this course is not easily extendable. In fact, practically, we do not extend it to complex geometries. We just change our approaches to finite volume or finite difference. So that is the short answer. Uh, However, your question about implicit or explicit still remains relevant. So let me, well, actually, we don't need to open that up. Basically, explicit solutions
So
still. So yeah, go ahead.
sorry to
Yeah.
disturb. Like I was asking, if the same problem,
Hmm.
which instead of solving using finite difference, and instead of solving using finite difference, if I solve using finite element, the same problem,
Hmm.
and will it be applicable for complex geometries?
Yeah, yeah, that is what. So let's just
Because example, what I meant to say is like we have this one-dimensional heat conduction equation, like double derivative of temperature with respect to spatial dimension and with single derivative with time dimension. So that we can formulate using this finite difference. And also we
Mhm.
can and even we can formulate using finite element. So you are telling like finite difference formulating that for complex geometry is not that good option.
Yeah,
And
so let's just quickly go through before like I'll come back to you.
yeah.
Let's discuss this even better. But actually, I think this would actually help. So as I was mentioning, this paper which I was following, it mentions some pros and cons. So it says that finite difference is easy to formulate and use, especially when you have prescribed temperature boundary conditions, basically Dirichlet boundary conditions.
Mhm.
But it violates local and global energy conservation, and it fails. It is difficult to use for complex geometry. But to just give you a quick flavor of how you could actually attempt to work around this scheme, actually there is a very nice chapter in this book which kind of answers your question. It is not that you can't extend it, it is a little cumbersome effort, and especially when your geometry is going to be for a commercial solver like ANSYS, where your geometry is something, it's a design parameter. It depends on the design, right? So what happens is in those cases, this finite difference based extension to complex geometry is very dependent on the geometry itself. So I'll show you what I mean. So there is some there is one figure which very nicely depicts this part of it. Let me quickly open that. Yeah, see. So this is the approximation that you can do in complex geometry in a 2D setting itself. This is what you can attempt to do. This is how your grid will start looking like.
Okay.
Okay, this is something that you can do, and if you think about it, it does make sense, because in this position you might think that this is just not relevant, but think about it. If your size of the square goes down, it is easily possible to actually cover this complex geometry. Essentially what you're saying is, if your geometry is complex enough, if it is complex, your grid requirement or your meshing requirement will significantly increase depending on how sharp your complex geometry is, right? And also I'm not sure if finite, actually it is very easily possible. Finite difference scheme works with non-uniform grids also. So they can work
Okay.
with non-uniform grids, but again, it is something to do with structured and unstructured grid, and especially in a 3D setting, again, it becomes a little cumbersome. So this is something that we can approach, but again, uh, as the paper mentions, it is difficult to use for complex geometries, and again, it fails when you want to incorporate higher order accuracies. So why higher order accuracies is important? When you want when you don't want very costly simulations. See, you want higher order accuracies so that with larger grid sizes, you can still get good uh, efficiency. No, not efficiency, good accuracy. But if you just approach it from a first order accuracy point of view, your grid sizes are going to be huge, because you won't be able to be accurate enough, because your errors are of the odd, they are large. They scale with the square of your grid size. So if you go higher and higher, your accuracies goes higher. So finite difference approximations kind of don't lead anywhere if we talk from a practical point of view. Whereas in finite element setting, the pros of the philosophy is that they can easily treat complex geometries, and even finite volume can also do it. It's actually very easy, or it's very easy. What do you say? It's very simple to visualize why a finite volume scheme would easily work with any complex geometry. But again, see, in any ANSYS software or any uh, CFD or I don't know, computational software, meshing becomes another issue, right? Meshing is something that you are not dealing with in this course. Meshing is itself is an important aspect of your CFD or computational solution, or what do you call it in solid mechanics? What do you call ANSYS mechanical? So that is,
Machine.
yeah. you call it finite element analysis. That's what you call it. So
Uh-huh.
FEA or CFD essentially, yeah, that makes more sense than finite difference. But the important thing there is, as you mentioned, because we are kind of solving a finite, we are solving PDEs, partial differential equations, and we do have implicit and explicit schemes. Like this concept of implicit and explicit does extend to these two finite approximation schemes as well. So because suppose your discretization can be done nicely in your 3D domain, but what if your problem is transient? Essentially there, uh, the idea of explicit and implicit uh, makes more sense, right? So there, if either your derivatives are depending on the next times on the current time step, or it depends on the next time step, or it's a combination of something. So you must have heard of Crank-Nicholson scheme. Maybe it's
Yeah.
covered in this course as well.
Yes.
So
Yes.
yeah, so again, it's the same point. When unsteady problems are there, then this concept of explicit and implicit does extend. So it's not that you're learning something stupid. It's just you're building up your base. You're building up your base, and then you can extend to it. So as you see that you see our discussion on live interaction sessions was on what do you say? Straight away we went into finite difference methods or finite approximation methods. But that is not what at least numerical methods are all about. There are numerical method is a much broader umbrella, where yeah, it's a much broader umbrella. So that is also something that is covered in this course. Yeah.
Okay.
So it is like a starter. You move to a course on finite element analysis, and you can pick it up there, or you do a course on CFD and you can pick it up from there. But
Okay.
but but realize that now you are kind of, whenever you go into deeper into those sections, you're essentially you're going deeper into the content of week 8. You're leaving all other things like week all 11, other 11 weeks, right? So that is there. Yeah.
Okay. Got it. Thank you.
You have any other questions or something you would like to discuss?
I think right now I don't like that was my question. Okay.
Okay. Hi, Apurva. Any questions for me?
Good evening, Sanjay. Not really. I watched all the lectures of stability and all. I'm comfortable with most of the things. Explicit,
Okay.
implicit, mathematics, and all that.
Okay.
The thing is,
Just
I practice. I tried writing the code. Theory part is okay.
okay. You have any issues with maybe some code writing or anything, or you're
No,
still working on it?
I'm working on it.
That's good. Oh, nice. Just one thing, because I was at it before you joined. Any do you have a feedback for me? Is my speed okay, or do you have any comments to make on the speed with which I do it? Because I feel sometimes that I am kind of rushing through things. I'm not writing things properly, kind of moving fast. But yeah, that I do that in pursuit of not wasting anyone's time. It's better to cover more ground than go slowly. But again, you can give a feedback. That would be okay. Yeah.
So it's fine. So initially, it was somewhat fast. I mean, you had started off with finite, this thing, difference, finite volume, finite element. That time it was fast, but gradually I was comfortable.
Great, great. So, okay, fine. So now we don't have much questions there. Also, the fact is that we kind of moved too much into like we extended last discussion too much, uh, like almost half an hour. So that is something where I have to redo kind of. I will have to redo because it does not make sense. 2.5 hours of what do you say? Both recording and watching is just unbearable. I realize that. So maybe we'll look it up. We'll work on SVD. So basically, okay, let me talk to you even like on this aspect also, because there are two guys now. And see, based on the course content, So where is the course content? I'm seeing that the professor ends the course at artificial neural network, and I was thinking maybe we can look into something for the next aspect, no, next 3 or 4 lectures. Maybe we can look into something on physics informed artificial intelligence or neural networks or machine learning. What are your thoughts, or is there any particular area where you would like me to look into or something? Or how do you like this proposition of maybe looking into physics informed neural networks?
Yes, that would be nice. But sir, I have a doubt in one topic. You discussed finite volume. You
Hmm.
had discussed. So, like the professor has discussed stability issues in finite difference. I'm asking about the stability issues in finite volume. I watched some other lectures. Like, can you briefly discuss something about Scarborough criteria?
Well, I've heard of it, but yeah, I'm not really sure. Let's see. Heard of it. Let's see. What does it say? Scarborough. I don't know the spelling also. It's solving linear equation using an iterative method. Okay. And, oh, is this what it is? Is it not called positive coefficient criteria? Hmm?
I mean, the positive coefficient criteria, is it just by observation, right? There's nothing much deep mathematics behind it.
So this one is saying that you have to sum it up, right? And AP dash is what? The present coefficient
Yeah,
of present, right?
the P node, one P node, I guess, and NB is the neighboring nodes, coefficient of the
Neighboring
neighboring.
summation of neighboring nodes. And positive coefficient says that neither of what does positive coefficient criteria say?
That all the coefficients should be positive or of the
All
same.
of them.
Yes,
See, I have maybe you can look. This is also a nice resource, especially for more advanced and especially on this stability, as you mentioned, no? Things like this. So this actually is a nice resource, and this is like 2 years. I came across this 2 years ago. I kind of bookmarked it. This is a good resource. Maybe I can put it up in chat. Okay, I maybe if not now, I will definitely discuss, or maybe I'll try to discuss things on Scarborough criteria. Or maybe let's look it up now only. Let's try to figure it now. But before I do that, let me just quickly go to the positive criteria, positive coefficient criteria. Okay. What does it say? That all A's should be positive. Okay. Okay. Actually, there is a nice book from that aspect. Actually, see, if you just want me to talk briefly on this, um, it is kind of it is kind of coming from the so okay, can we be doubts about this,
can you
or
repeat?
just you? So so I was just asking if your question is how does this criteria, just like how did we come up with this criteria, or
Yes, yes,
is
sir.
there something else that you want to?
Yes,
Okay,
yes, that,
so
that's what.
from that point of view, actually, I have a good answer to that, but I will have to look it up. It's somewhere. Let me see. Numerical methods summary of. Don't know which. There was a book which I had from finite difference. Let's see. Is this the book? No. So essentially, let me quickly talk about it. I will talk about it in a wavy, hand wavy manner, because again, I'm not prepared anything to be strict, speaking things in a strict manner. But essentially, what is happening is that we take a sample problem with which we know our analytical solution for. So, and I think this problem, uh, yeah, I
If,
think it is the unsteady equation only. So this one, it depends. It depends on what equation you're kind of solving. So what essentially, let me just quickly write this out so that you can. Okay, so this is the unsteady parabolic PDE uh, that we're kind of trying to solve. And suppose we know this solution to it. Actually, for certain cases, you have an analytical solution for it. I think for this one, we can actually find the analytical solution for it. Right
yes,
now,
hate,
people. Hmm, go ahead.
yes, I hate equation. It has analytical solution.
Right? This is a simple problem where all coefficients are constant and you will have a nice initial condition, and then and again initial condition is very important here. Otherwise your solution becomes more complex. In those cases you can find your analytical solution. Now what they do is they start to try to solve this using again your finite difference scheme or finite volume scheme of that sort. And they kind of do it this they kind of see how uh, when does this solution or when the scheme starts to fail. Okay, and they also try to quantify the error in your local error or error distribution. So error is a function of time and space, uh, as a function of your grid size and yeah, grids, basically grids. And it is from there this whole idea of criterias come in. So even positive coefficient criteria comes from that logic only, because actually this we can actually go through this. But just before I do that, I wanted to just show that book also. I don't know if that book is somewhere. Partial or somewhere, I don't know. Numerical methods. Book. Let me see. This is the book. I'm not sure. Let me check. We have a free copy here. Free copy is also an issue, right? It's not available. Let's stick to whatever material we have. Numerical methods is called, huh? Let me try once because I think I have that on.
Or if you wish, we can discuss it next week.
Yeah, maybe I'll do that now. I'll do that later. Okay, let's quickly see what is this. Okay, let me just quickly go through this. So analytical solutions for certain systems can be difficult, and the numerical solution based on integration of this thing results in a system of algebraic equations. These algebraic equations are usually referred to as discretized equations. Uh, okay, this criteria comes from where? Okay, so as I was saying, let me just quickly, at least in principle, show you where this entire thing is coming from with the help of positive coefficient criteria. So essentially, we know that our differential equation or our partial differential equation will essentially uh, come in this format, right? They will have nodes. So x is the unknown variable that we want to find out, and the a's are the coefficients. Okay, so now they introduce x min and x max, and just by the sheer logic, they say that if you multiply x min with this kind of with the summation of all coefficients, and again x max, so you know that uh, this entire sum will lie in between these two products. And now note that the above is valid only when okay. And then this whole idea, see this is only valid if you have the entire sum is positive, right? If the above is only valid when all are positive. Let me think if otherwise, if one is negative, yeah, it makes sense, right? It is if all are positive, only then we can write this entire thing. And now if we write this, now let's quality in 7.21 is obtained when x. So in the case 7.20 in this, okay, suppose that the summation is 1. Let's say we kind of divide everything by the summation. So rather than saying this is 1, let's say this coefficient sum of all coefficients is some value, and we divide the equation by this sum of coefficients. So we will be able to get this kind of thing, right? Whereas will be a little distorted value, but it will be of this sort. Now let us now apply 7.21 on the difference equation. This is there, uh, meaning that uj is restricted by the extrema. All thus will not have the ability to grow without the bounds. So okay, let's just go one more step before. So in this case, the coefficients are a1, a2, a3, and such that the sum of the coefficients are a1, a2, a3. So what have they done? 7.21 on the difference equation, 7.16. So essentially what they have done is, suppose there is this equation that you have. Okay, this will come from some problem. Let's look at that problem. So suppose this is a co-ed flow problem. You have this kind of situation. Now, if you solve for this, you will find this. This is the governing difference equation that you will have, where D is also given. I'm going quickly because again, going over these things in a hand wavy manner. So essentially, what I'm saying is essentially you will have your governing equations or governing difference equations, or yeah. So AX equals to B kind of situation in this format only. And now let's see when and you look at it, uj n plus 1 uj. So basically you're evolving in time. So n plus 1 is the uh, is
And
the is the time step, and j is the position step. So we're kind of moving forward in time, and what it is saying is, in this case, suppose in this case, see, in this case it follows that a1, a2, and a3 are all 1. Okay, so we can actually apply our we can quickly apply our positive coefficient criteria in this formula. And then what essentially we are saying is that if because in this equation it follows that uj plus uj n plus 1 um, will be in between the minimum of these and maximum of these. So it will kind of converge. You see how it will converge, kind of. It cannot move away out of this range. It is bounded in a range. And so essentially it can oscillate in that range. That is definitely true. That is something that can happen. But suppose that this range also continues to converge, so we are sure that this stability is going to come. So suppose meaning that uj n plus 1 is restricted by the extremas of uj n. Uh, right? So suppose your velocity, you have some initial velocity, and uh, at n equals to 0, in the next time step, all those values are going to be between two the extreme values in the initial condition. So and so you are not going to be unstable. You see how the idea of instability is coming in. All the solutions at the previous time steps will thus be not will not have the ability to grow without bounds and therefore will be stable. This stability is actually this is a Lyapunov stable condition. That does not matter to you right now. Let me not introduce new things, but essentially it is not unstable. At least it will be bounded. It is bounded. Okay. The condition for stability for all coefficients are positive. As d is positive, this means that may be negative, and the condition for a3 to be positive becomes d should be less than this thing. Okay, and then the condition for stability becomes, so this is how he derived the condition for the stability by using the positive coefficient criteria. Okay, now why I discuss this entire thing, which is not related to Scarborough criteria. What I essentially wanted to show you is what we do is we take a model problem, we apply numerical methods to it, and then we look into this criteria. This C D was a what do you say? I think Crank-Nicholson number, Courant number. I think that is what it is, right? No, uh, it's not Courant number. It's something else. It's a Fourier number, let's say. Okay.
Yes, sir. Fourier number.
Yeah. So now, essentially, what are we saying is that this D value characterizes your numerical scheme, or at least the grid sizes. So what essentially every analysis and numerical method will overall do is they will take a model problem, they will analyze how with different discretization and grid spacing, how much your error is your error bounded or not. You do stability analysis on it, and from that model problem itself, you kind of say that this follows, right? For example, I'll give you an example. A lot of times some numerical scheme says that the Courant number, you've heard about the Courant number, right? U delta
Yes,
t by
sir.
delta x, right? People say that Courant number should be less than 1. Only that is physical. But there are problems where Courant number can be larger than 1, and still the problem is solvable.
I've come
Sometimes the
across,
Courant hmm?
I've come across that, sir. It's Rick Meyer scheme, something like that. Rick Meyer, no, beam warming. There's something
Which
called as
one?
beam warming scheme. Beam warming.
Beam warming. I've not heard of these things. Beam warming.
Beam warming is there, then one is Rick Meyer scheme also.
Okay, beam and warming. Okay, okay. Yeah. So as you mentioned, there are so it's a lot of people have given a lot of see, this is the criteria. I think your this thing should be less than half your CFL. So this is the crank. No, what is it called? CFL is what?
Courant Frederick Lewis.
Yes, yes. So CFL number or CFL should be less than half. It seems here in this case. Now, there are problems where with a CFL of, let's say, 5, also your problem will reach the solution easily. Okay. And there are problems where your CFL number or your Courant number has to go close to 0. Okay. And only then your solution will be stable. So these are kind of I will not say they don't work or they don't give you anything, but they are essentially not applicable everywhere. That is all. That is, they are not at least strictly applicable everywhere. So for the very simple case of positive coefficient, this thing, positive criteria for positive coefficient. This is the conservative. What do you say? Conservative criteria. If this is true, your entire solution is definitely going to be asymptotic. But it does not say that if your positive coefficient criteria is not met, your scheme will be unstable. So it is kind of it's a sufficient condition but not a necessary condition, and that can be true for even a Scarborough criteria. My whole point was also on that. So maybe actually, let's ask ChatGPT also. Can you derive Scarborough criteria? This guy does it very nicely. tab. Okay, so let's ask ChatGPT once. Does it say? Yeah, whatever the spelling is. So I know a few possibility. No, not in numerical method. So as you mentioned, right, you said that it is something that you wanted to study, find like stability of a finite difference scheme versus stability of a finite volume scheme. But note how in our interaction sessions we have looked at that essentially both the problems will come into this AX equals to B format. So both criteria might be relevant to might apply to AX equals to B, and it is not method specific criteria. It might be the case. So anyways, AX equals to B, this thing will follow. So gave a practical test based on a diagonal dominance. Consider an equation from the system AII This thing is there. So he has considered a full matrix. He has not considered a tridiagonal or anything of that sort. So now rearranging, you will get this thing. In an iterative scheme, the new value of xi depends on the ratio of aij divided by, so mod of aij divided by aii. Scarborough criteria for each equation I, define the row ratio. This is the row ratio. Sufficient condition for convergence is Ri is less than 1 for all I. Practical rule is it can be equal to 1 also. If the coefficient matrix A is strictly diagonally dominant, then Jacobi and Gauss-Seidel methods are guaranteed to converge. If Scarborough criteria is not satisfied, convergence may still occur but is not guaranteed. So as I said, it is not guaranteed, but it might. So it's not a necessary condition. But let's understand two things. One, what is a diagonally dominant matrix? Dominant A, and two. You have any other questions to ask GPD? To how do we arrive at I less than one condition from AX equals to. I'll also quickly take a small break. I'll just come back, okay? So. Okay, so what is a diagonally dominant matrix? A diagonally dominant matrix is of order is said to be diagonally dominant if summation mod of, okay, that is, wait, it's this criteria follows for only diagonally dominant, huh? Scarborough criteria. So this is also a good example of something what Yashod asked, that whatever we are kind of studying in this course is relevant. It's definitely, it's not finite difference is not something that you will deal with, but these criteria of the sort will still apply in schemes like finite element and finite difference, because these criteria are scheme universal. Okay, so okay, that is fine. So what does it say? So it says that based on diagonal dominance. Okay. So basically saying that if your matrix is diagonally dominant, then you are going to get a stable solution. That is what the Scarborough criteria is saying. Okay, right? That is in each line. The error in the iteration is x minus xk. Okay. The new error depends on the size of the ratio aij by aii. Let's see, why does it say so? The new error. The new error. Okay. So, Apurva, you there?
Yes, sir.
See, if you read through this, it is kind of saying similar stuff. So, what is it saying? So, essentially, I'm just reading, like, I'm just following what GPT is saying because I don't have a textbook to follow right now. But, anyways, so it is kind of saying that xi depends on 1 by ai, I, and then bi minus summation aij xj. Okay, so maybe I can use the similar idea from what positive coefficient criteria used. Suppose you have your initial conditions, or uh, suppose your true solution has a minima and maxima in x. Okay, suppose x true, uh, min is x min, similarly max. Right now, what else can we say here? It is more or less like it is a, we can feel for it, but I'm definitely sure that there is a proper proof. Maybe let me look it up. But at least let's take a feel. Let's take feel. What is kind of what it is kind of saying. So at least we can imagine in the case where AIJs are very small compared to AII, we know that this value is kind of gonna converge to BI by AI, right?
Yes, sir.
Now, suppose they are large. So in that case, suppose AIJs are large. In that case, we know that it will kind of converge. How it will? It can diverge. It can have the tendency to diverge. BI AII, and then it can kind of diverge by this value AIJ by AII XJ. Now, this, and also summation is there. We can't actually take this thing out actually. Okay. So mm, now we can look at this stuff, right? Yeah, actually we can actually proceed with this. So now this term, let's call this term as t equals to some this thing. Now what do we know? T is supposed to lie. Uh, will t always lie like this? X. So do you see that can we have a bounded approach kind of can we bind this in between some values? I'll have to think about it. How do I bind this? Let me think. So okay, maybe uh,
So
this is a dot for hmm.
for this positive coefficient thing, I watched a lecture in that the professor only gave a sample equation. He just showed that if the coefficients are negative, then boundedness cannot. If the coefficients are of different signs, then boundedness is not possible. If the coefficients are of same sign, then boundedness is possible. He just, but he didn't give any mathematical reason. Just observation. It
Yeah,
was just an observation. That's what I thought.
that's yeah, that is actually the thing is it is at the end of it, it is the case. Because you see, if we had a hard proof, then what would it mean is that if you are violating positive coefficient criteria, your system would be unstable. The thing is that it is not a regressive, it is not a, it is kind of a test. It is not a proper, what do you say, a proof. And essentially, where do they come up with this kind of inequalities? Is that they consider a model problem. They'll say for this model problem, this and the model problem will have certain features. So for example, this model problem is a parabolic PDE, right? And it kind of encompasses a lot of different PDEs, right? Alpha can be positive or negative and stuff like that. Now, what do I mean is they will consider this solution. They will do a hardcore. Actually, that is why I wanted to find that book, which I'm not able to find now. Um, what they do is they will look at they will properly solve it, and they will do a full strict derivation of how your error propagates when you do it. Maybe Scarborough would have also done it. Let's also look it up on uh, some paper would definitely discuss this. Let's see. Scarborough criteria. So that's the numerical mathematics. See, here's a book on. Let's see if he mentions that, and I'm pretty sure it's his book would cover this. Okay, let's see. 1932. So let's see. Short note only, huh? I don't want short note. I want full. Okay. Okay, let's quickly see if we can find something. Oh, I have to buy this book. I can't buy it. On the convergence of iterative methods. Let's see. Definitely, his book would cover something on this. And as you can see, they have done a full thorough analysis. At least we can uh, frame that from this book. At least first few pages of this book. Method of solving. Okay. Utilization equation. We will have to do this whole full proper this thing. That is why these things are not covered properly in courses like this. Like these are very mathematical steps that you will have to take to prove or at least come up with these inequalities. So let's discuss, just to quickly look at it. Results set by equation 20, usually referred as, okay, so this is the whole derivation, as a sufficient condition for convergence. You're saying something?
Sir, can you share this in chat? Because I've gone through a few CFD books also, and they just only mention the condition. That's it, not much detail.
What have you shared? What have
So
you
can you
shared?
share this? Can you share this book in the chat?
This which book?
This one, sir. This one.
This paper, huh?
Yes, sir. Oh, paper.
The paper only. I will share it. Wait. So you can look it up, but again, it is a little tedious, it seems to me.
Yeah,
So
I'll just skim through it. Some feeling I'll
yeah,
get.
that would be, yeah. It is a good. It is good to have some feel. That's true. Actually, I was also interested at some point of time. How do they come up with these relations? Yeah, it's a little complicated. So the process of iteration will converge if in each equation of the system, the absolute value of the largest coefficient is greater than the sum. So Patankar mentions, I don't think Patankar mentions this, but sure. You read this book also.
If it is mentioning Patankar, then I'll check once because I have not gone through that book.
Patankar, I don't think Patankar has Karpov, especially the book he has mentioned. Let me open Patankar books. Then Patankar must be somewhere numerical. Hmm. Patankar, does it discuss stability properly? I don't think so.
I've not gone
I've
through it
not,
properly.
maybe. I also have not gone through Patankar properly. Actually, this is a nice book for numerical methods. This is a book which one can actually But again, this is also finite difference only, or maybe finite volume. But yeah. Anyways, this maybe we can look it up. This one also. But essentially, this is the statement they're making. They're kind of making a conservative statement. But how do we prove that statement itself is also a challenge? It's not straightforward. That is also true. This one, I get not okay. Okay. So at least we can read the statement. That is the least we can do. The process of iteration will converge if in equation of the system the absolute value of the largest coefficient is greater than the sum of the absolute value of all remaining coefficients in that equation. That in a mathematical form for non-negative RNB coefficients is this. What is different and more restricted than this criteria set by equation 21. The books. That this seems to be a nice paper. Let's also read the conclusions also. Convergence of the iterative method to obtain the numerical solution of it answer. With this objective, clarification discussion is made on the next. Okay, so maybe we can look with this looks too complex to me. Discuss in a session like this, but maybe I have pasted the link in the chat. You can go through this if you would like. Okay, let's come back. You have other questions? Want to discuss something else?
No, sir. No, sir.
Okay. I'm also not totally working into numerical methods. This kind of gets into more technical than textbook stuff. So sorry, I'm not that helpful in these things.
No issues, sir.
Yeah. Anyways, okay. Before I get into singular value decomposition, that is what I have planned to discuss. I actually wanted to show one paper with. I recently went to a conference and I stumbled upon a paper on singular value decomposition. So what they do is they've just they're not done much about the problem, but what they have done is they have simulated flow past a cylinder in a CFD tool and just done a singular value decomposition to see how what does it give. That's it. That is what they have done, and it is quite interesting to look what it does. Okay, so they talk about the singular value decomposition. Uh, I would like to rather talk about this flow past cylinder system. So it's a canonical problem. Nothing very fancy there. And as you would know that the solution changes with depending on what the Reynolds number is. So in this case, this guy has taken a Reynolds number of 100, which comes in the range of vortex shedding. So shredding, okay. Yes. So RE of 100. So vortex shedding kind of happens, and he has considered the unsteady. He has simulated unsteady simulation. So let's just quickly, and as you might be aware of, I mentioned the fact that there are singular values associated with. So if he considered only the first singular value, he got this data with only one singular value. When he applied the second mode, just looking at the second, not adding the first mode to it, this was his result. And then the third result kind of, you can see some vortex shredding phenomena is available in mode 3, whereas mode 1 is kind of having this wake dynamics with it associated with. When he combines uh, the CFD solution with the, what do you say, the reduced order data, you can't actually figure out a lot of difference from it because the important modes have been considered here. So let's see what number of modes has he considered when he has plotted this data. So okay, so he considered the first 20 modes to construct this SVD data. So he realized that actually the first 20 modes are actually important, at least when he wanted to present it in the paper. The first 20 modes were, it seems that were important to actually uh, get the exact picture. I think the error is also something that he must have plotted, no? He has not plotted the error. The paper is quite small. Just wanted to show you again an important advantages of importance of, like, it's actually very fancy SVD. Okay. The interesting part here is also see the first mode is able to give you 99.2% of energy in the entire system, whereas the next 20 are just giving you minimal input. Like the first three nodes, 4, 5, 6, maybe seventh or eighth node, you might have, or the first 10 nodes, you're done. It's almost 100%. So that is actually nice, right? Again, the term energy and stuff will depend on the context. So just we can understand energy is something that represents the accuracy of the solution. So we can kind of say that the first mode is 99.2% accurate, whereas as you go further, you are getting to as more accurate as possible. Okay. So yeah, that's there. Then okay, let me close this. Okay, yeah, let's come back to this video. Actually, I wanted to discuss how does SVD, like the idea of SVD is also quite complex. It must be like we should acknowledge or realize that SVD is kind of not trivial. So you have some metrics and you will have uh, this kind of construction. This is how they put it. U is a orthogonal matrix. So U Then so U is an orthogonal matrix. Sigma is a rectangular diagonal matrix. VT is the transpose of V. V is also an orthogonal matrix. Now I presume that you might not be aware of orthogonal matrix or stuff. So maybe I'll talk a little bit about orthogonal matrices to begin with. I think the correct definition is orthogonal matrix is generally represented by this symbol Q. And when operated on any vector, it will give you V, but there are two things that happens with orthogonal matrices, that their norm or the length is preserved, and also I think QU dot, so QV also stays U dot V. So the angle is also preserved. You put it V. So essentially what you're doing is that you're kind of rotating, in some sense, you're kind of just rotating the vector. So as I had mentioned earlier, that a tensor or a matrix for that matter, what essentially it does is it transforms a matrix orientation to another, and in meanwhile either, and in the way it can either scale it, rotate it, and stuff. But orthogonal matrices are what do you say? They are like they don't scale. They don't do any scaling of that sort, and so your length of the vector remains unchanged. That is one thing. Let me open up like that. Let me be precise with this. Yeah, actually, there's a third definition also. Like actually all these three properties are maintained, but orthogonal metrics are characterized by this thing. That is actually better. I forgot to mention that. This is actually the criteria for orthogonality. If a matrix is orthogonal, then this will follow. And yeah, it's nice. So okay. What else? Okay. So there is this orthogonality that we can talk about a little bit about orthogonal tensors or matrices, but maybe let me move quickly. I'm thinking to end the class today, like early 7:30. Uh, okay, so maybe I'll not talk too much about this, but let's quickly talk about symmetric matrices. So symmetric matrices are very nice, and that this is where the power of singular. I feel singular value decomposition is kind of getting its power from this itself. So let's quickly look at it. See A transpose and A transpose A are quite special formations. They are actually quite special. And let's just quickly appreciate this before we kind of disperse. Okay. So suppose A is a matrix of M cross N. So can someone like only think Apurv is there? Yeah, he is there. M cross N. So just can you quickly tell me what these two matrices will be of? Like what will be the dimensions of it? This will be M cross N, and this will be M cross M and M cross N. Now important things. First of all, they become tensors. So even if your A is a rectangular matrix and it does not fit in the construct of a tensor, A transpose and A transpose A, both of them do become tensors, first of all. That is important. So essentially, they are only dealing in one space. They're kind of um, so there is no null space, or there will be some null space, but definitely it's a tensor, right? It is it's its domain and codomain are in the same dimension. So it's in this dimension. So what am I saying is that where A will transform a vector in R to the power n, not R to the power, script double R, I think. So you know about this, right? So A is kind of moving a vector from R to the power n to R to the power m. But these two of them are kind of they are moving in the same region. So A transpose is still is having it in only M domain. So its domain is also M and its range is also M. And whereas A transpose A is doing it in R to like in
Correct.
n dimensional space. Uh, Now, why is that interesting? First of all, it now becomes um, like it is a more what do you say, more favorable, more preferable setting. Okay, A transpose A and this thing, because tensors are more mathematical. We kind of have more understanding of them. Rectangular matrices are a little, at least for me, it is a little difficult to relate with them. Especially geometry becomes difficult. Tensors have a geometrical understand, like a geometrical um, picture. They have a geometrical significance. I don't know if probably matrices will also have a geometrical picture, but definitely tensors have a better geometrical picture associated with them. Now, the important part with these two matrices are that they are symmetric, and symmetric matrices are also very, what do you say, very powerful. We at least that is something that we can actually see. So A transpose A is actually its own transpose. That is the beautiful part of it. So wait, what happened? What is going on now? Okay, so Apoor, you know what is the formula for A B to the power T?
Yes, sir. B transpose A transpose.
Yes. So if you just quickly apply that even there in the top, you will quickly see that this matrix is a wait. Hmm, mentioned this incorrectly. This should be. Yeah, so this is the definition of symmetric matrix. This is the definition of orthogonal matrix. Sorry, I wrote it as a symmetric matrix. So orthogonal matrices are not symmetric matrices. This is the definition for it. So anyways, so you see that if a matrix has this kind of property, it is symmetric, and this will follow for both A transpose A and A transpose. Now, now what else? Yeah. So now why are they powerful? Now, the reason they are powerful is that they have a spectral decomposition. So, what do I mean by that? Suppose uh, S is a symmetric matrix, then it follows that we can write this thing for S. Uh, it's called spectral decomposition, I think. Spectral decomposition. Yes. You write it as lambda 1, where lambda is your eigenvalue. Again, square matrices have eigenvalues. Rectangular matrices don't have a construct of eigenvalues. So now we are in a comfortable position. We like the picture of eigenvalues. So yeah, that is one thing. And now what I'm writing here is a tensor. A tensor. It's a tensor. Okay. Dyadic product. What is the symbol for dyadic product? Mm, okay. Now I am sure. Are you aware of this? Whatever I have notation I have written. Are you aware of what is this?
I'm not aware of the notations, but I'm aware of dyadic product.
You're aware of dyadic product. Are you aware of spectral decomposition?
No, sir. No, sir.
Acha, okay. Do you understand that S or any met? See, a tensor A will have. You understand tensors because you're there. I'm just kind of trying to
Yes, sir.
explain it to you. So now you understand tensors are Aij. Uh,
Yes, sir.
you write Ei cross Ej, right?
Yes, sir.
You write cross, right? Don't remember. You
Cross
write
EI in EI and EJ will be the unit vectors.
Ej. Just give me a second. Let me think. Is it this? I think it is this only. This is how you write. Let me quickly check this out. What do you write? I think this is how you write it because if you write AU, if you do it AU, then what you will get is AIJ, and then EJ takes the dot product with U, so you get UJ, and then EI. Yeah, this is the right way to. This is right. Let me just bold this thing so that we know this. These are vectors. So you're comfortable with dyadic product. So now essentially this is one way to write it. Is this a comfortable statement for you to digest?
So why there is a cross product there?
This
A
is not
equal
cross. This is not cross. This is dyadic product. You said you were aware of dyadic products.
this notation I've not seen. So that's okay, sir.
Okay.
But I understand what it.
Actually, I'll just write this down. What does this dyadic product also means? So it means it's essentially this. It's a tensor that you make out. It's a tensor that you can form using two vectors. So what this essentially does is, suppose this is a tensor, right? Suppose this is this tensor and you multiply with some vector, let's say A. So essentially you write this as U. This is the definition of your tensor. This is how a dyadic product, this is what it means. So in this case, if you just look at it this way, it's just one way of writing this, okay? This is just one way of writing this entire thing. If you look at it, if you just substitute this thing, essentially what I have written is AU. What I have written is AU is AIJ U, then dot times EJ EI. And you know U dot EJ is UJ, right? This is just a fancy way of writing this thing. If we consider a 3 by 3 dimensional scenario, let's say I consider, let me just show you how, and suppose we have this, suppose E1 is this. So then, suppose this is there. This is just a fancy way of writing things, okay? Don't get uh, like Don't get scared of this new way of writing
Unit
process.
vectors, right? Unit vectors.
Unit vectors, right? But it is important. It's yeah, it's a unit vector. That's okay. Now, if I would have to write this thing, this one, then this is how it will look like. If you do it out, if you do this thing out, you'll realize this is the only matrix that has this property. This property. This property. Maybe I'll color this property. This is the matrix that you will generate. Okay. Suppose I want to find, suppose this is the matrix I'm saying, right? This is the matrix. I'm saying this is a matrix. Now I want to find the units of this, what do you say, the entries of this matrix. So what I will do, I will put, I will, so one, if you want to find the entry of a matrix, what do you do? If I want to find Sij or Aij for that matter, are you aware that we can write this thing down? Ei Aej. Does this make sense to you? Essentially, what I'm saying is that you multiply, you only consider the jth element and you multiply and you keep it at the ith position. So, like, are you aware of this?
No, sir, but I think it makes sense. I'm
It
seeing
makes
it for
sense, right?
so.
So, if I just apply this to this entire thing, what you will see is ij will become uivj, sorry, uivj. And so for this one, ei, this one, the ijth column will be, you know about Kronecker delta, right?
Yes, sir.
So delta 1 I and then delta 1j. That is how it will come. This is ijth element. Now the important part which I just wanted to discuss was if you substitute this entire thing into this thing, there exists basically what I'm saying is because every symmetric matrix is diagonalizable. So in some form, in some basis, in some you what do you call coordinate system, you can actually write this thing for a, 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 a symmetric matrix. Okay. So but it does not happen in your coordinate system. This will not happen in E1, E2, E3 coordinate system. Let me be uh, explicit about that so that is not confusing. It will happen in some distributed coordinate system. Okay. So why I'm saying this is suppose your coordinate system, you kind of rotate it or move it. You know the entries of the tensor will change, right? Entries of the tensor depend on the coordinate system.
Yes, sir.
Isn't it?
Yes.
Now, in some convoluted or some basis vector, which will be defined by E1, E2, E3, let me put this as E1 star so that this is not confusing. This is not like the normal E1 and E2. These are like special, like this E1 star, E2 star, and E3 star are forming a basis of their own. They're definitely a orthogonal basis, but they're kind of rotated. They are kind of they're not the 1 0 0 0 1 0 and 0 0 1 uh, vectors. They can be different vectors, but they will be unit vectors and orthogonal. In that frame, in that frame of reference, your every symmetric matrix has this property, this lambda 1, lambda 2, and lambda 3 diagonalizable property, and kind of this is where this diagonalizableness is coming. Okay, this matrix is also looks like something like this. Okay, it also looks something like this. Indeed, what you will note is, let me put, let me see. So just so they will also have, and indeed they will have, you know what, they will have this kind of situation. They will be squares. They will be like square terms like this, and other terms are zero. So this is how that diagonal term in SVD looks, and these are the diagonal values which we are kind of capturing. And okay, that is what it is about. I've not properly shown it, but anyways, I think you get the idea. Maybe we'll discuss this more in detail later. I'm gonna close now. Let me think what I was gonna mention quickly. I wanted to mention something. Yeah, so essentially, this only symmetric matrix has this very nice property, and this is why this A transpose A and A transpose have this kind of nice decomposition possible. Okay, this decomposition is coming from this whole idea, and what you can note is if your A transpose has some diagonal values, they will kind of get square rooted if you reduce it, because you see A transpose is kind of a squarish concept, right? So that is why this squarish term also comes in. Maybe we'll talk about it more in detail next time. What I will just quickly show you is that next time uh, we'll quickly discuss one important thing about SVD is that it is very stable in the sense of numerical convergence, especially when your matrix is ill conditioned. So I'll show that to you, especially when calculating pseudo inverses or inverses. Um, LU decomposition will fall flat on its face, whereas SVD will work very nicely. And second thing is that I'll just quickly discuss, because let's see what I wanted to discuss. One decomposition I wanted to show, which is very nice, which something which we can nicely see, is the decomposition called as polar decomposition. That gives you a good feel of how SVD will kind of like it gives you a feeler of how SVD arises. Okay, so in a singular value, in a polar decomposition, you basically write that any matrix can be any tensor, now not a matrix, any tensor can be written as Ru, where R wait, yeah, R is a orthogonal matrix and U is a symmetric positive definite symmetric matrix. Okay, so it's kind of a A B kind of situation. So this decomposition happens, and you see this Ru, right? This is the orthogonal part of it, and U has this what do you say? It's a symmetric matrix. So maybe it makes sense that we can further break it, but again, SVD is for a rectangular sense, so directly does not extend. So polar decomposition directly does not extend to SVD, but it kind of can give you a feel for SVD. So this is where we can discuss that part of it. Again, we are not discussing hardcore linear algebra, so it is difficult for me to cover this in detail. We can just quickly discuss this part of it. But actually, it is nice to understand how come this thing is arising. So maybe we'll discuss that part of it. Then yeah, let's see what else we can discuss next time. So I'll close now. Okay. So thanks Apur for keep joining. It's always nice to interact. It's always nice when someone is there. Okay. We can log out.
Okay, sir. Thank you.